On, and today we'll talk about language modeling, which is one of the basic technique in information retrieval. So our outline will be to learn some of the basic stuff, how to work with the electronic text, of course, for information retrieval systems. And our main topic today is going to be language modeling. For all the examples in today's lecture and in the coming few lectures, we will use the Shakespeare's work as an example. All of you know that Shakespeare is a very well-known author and writer, and he has written many excellent pieces of writings. So we will take his plays as the example text to apply the techniques that we study in information retrieval. Like here you can see an excerpt from one of his plays, Thunder and Lightning, Enter Three Witches, First Witch, When Shall We Meet Again, and so on and so forth. So our basic text corpus will be from the plays of Shakespeare for applying the techniques of information retrieval. Human language data is the raw material for information retrieval systems. All IR systems work on the human language text or data that we also studied in the last lecture. So if we want to build an information retrieval system, we need to have an understanding of two things. First, the electronic text format, and the second is the characteristics of the text that these data or these formats they encode. So just like for any language, if we want to provide some information to someone, we need to understand the language, the characters, the words, the vocabulary, and the sentences, and then the grammar, the rules, how to construct the sentences. So similarly in IR systems, we need to have an understanding of the text format and the characteristics of these formats that helps us in understanding and then processing and retrieving the information. We'll talk more about both of these things in the coming lecture, in the coming slides, inshallah. So talking about the format, there are two key aspects of every document. The first is the content and the second is the structure. As I just said, the first thing is to know the characters, the words, the vocabulary, and the second is to understand the structure or the formation of the sentences or how these pieces they are connected together to make some meaningful information. So let's discuss more about content and structure. First of all, content. What is content? It is simply the sequence of words in a document. So this entire thing on this slide, it is the content, it is the actual play of Shakespeare, Thunder and Lightning, Enter Three Witches, First Witch says something, Second Witch says something, and so on and so forth. So it is a sequence of words in a document that will be processed in the later stages. Structure. There are many things that help us in understanding the words. Every textual document has a particular structure. Like it may have lines, it may have line breaks to make a new line, the page breaks for new pages. Talking about these Shakespeare plays, we have labeling of speeches with the speaker. Like if I go back to the previous slide, this is the label, the First Witch. So this is the label of the speech. This is the label and this is the speech. This is the speaker, this is the speech, and so on and so forth. So we can have labeling of speeches with the speakers. Stage directions, again talking about the Shakespeare plays, we have stage directions, how the play would be set up, what will be going on to perform this play. For every actor in the stage, there are some directions that have to be performed by the actors or by some outside people to make an attractive play. Act numbers, scene numbers, page numbers, and so on and so forth. All of you know that every document has a specific structure. Like if we talk about Microsoft Word, then every Microsoft Word document has a particular structure. Every Word document must have a title. Every document has headings. Every document has subheadings. Every document has sections, pages, paragraphs, bullets, tables, figures, and so on and so forth. Similarly, if we talk about Microsoft Excel, then Excel has its own structure. It has cells, it has rows, it has columns, it has tables, figures, and so on and so forth. Similarly, if we talk about PDF, it has its own structure. So every document has its own structure, and if we want to make sense of any text in a particular document, we need to understand the structure of the document. As we just said, if I go back to the previous slide, this is the structure of the Shakespeare's plays. So every play has these components that make it a play, right? So there are many different kind of formats like Microsoft Word, HTML, XML, LaTeX. This is one of an important format that you need to know about, especially if you are in masters or you go for research. So this is also one of your reading assignment. You will see what is LaTeX, why it is important, MIF, RTF, PDF, PostScript. There are so many formats. Now talking about information retrieval systems, HTML is one of the most commonly used format in all the information retrieval systems. I'm sure all of you know about HTML. It stands for Hypertext Markup Language. So it is a markup language, which means it is used to mark up the content with some tags. It has a fixed set of tags for presentation of the document. As you can see, the main purpose of HTML is how the documents look for the human beings. So the pages are linked via hyperlinks. So as the name implies, it is about hypertext. So we have hyperlinks between the document, anchor text that describes the contents of the pages. So it has a fixed set of tags, like it has head tag, it has body tag. You can have different level of headings, H1, H2, H3. You can make tables, you can give captions of the figures, you can define the table rows, columns, and so on and so forth. So the thing is, in HTML, these tags, they are fixed. You cannot define your own tags. So all the tags in HTML, they are fixed, and their main purpose is presentation, how the document looks on the screen. Another important format for the documents is XML, Extensible Markup Language. So it is based on the idea of separating the content and the presentation. So I believe all of you will have gone through this frustration. Sometimes you have a document in one format in Microsoft Word and you want to change it to a different format, and you will agree with me that it is a very tedious process. It is a hassle to change the format of document from one to the other format, from one to the other template or the other style. So the idea of XML is to separate the content and the presentation. If I have a separate content, okay, and I have separated the presentation, how this content will look like on the screen. Whenever I have to change the presentation, I can replace it with a new style, okay, and I do not have to touch the content at all. So probably all of you are aware of CSS, cascading style sheets. It is one of the commonly used technique to define the format of the documents. So you can attach any CSS with the XML document to render it the way you like it to be rendered, right? So that these descriptions, it focuses on describing the content via metadata tags. So here in XML, the tags are not fixed. Their purpose is to describe the content, to explain the content, right? So the description will vary from one to the other document or the other requirement. So you can define your own tags and then attach them with any document. These descriptions help in understanding logical structure of the document. So every document has a logical structure. Just like we now saw about a play, every play has a logical structure. Similarly, every document has a logical structure. So these descriptions, they help us in understanding the logical structure. And the physical structure, how it is rendered, the presentation, it is like the font, the color, layout, etc. It is defined separately. Like here in cascading style sheets, you can define your own presentation and you can change it whenever you like without having to need to touch the content, right? Like here, if you see, we have annotated the play with the metadata, the tags in XML. For example, at the top, it is a stage direction. So from this tag, I know that it is a stage direction. What will happen? There will be thunder and lightning on the stage. So the directors, they need to create some sound, some light, thunder and lightning, and 3 witches will enter the stage. So next we have speech. So from here to here, there is a speech, here. This is one speech. So, and this is the speaker, first witch. So first witch is the speaker. These annotations, they help me in understanding what is it. So it is a speaker, and this is the first line she will speak, and this is the second line she will speak, right? So you can see that with all the content, in the previous slides, I had shown you the content. Here we have attached this metadata with the content, the XML tags to describe the content, which makes anybody very comfortable in understanding the content. There are many other file formats, like there are binary formats. Every system can define its own binary format, which is in the machine language. We have PostScript, PDF. There are so many other text formats that are used in the information retrieval system. And we will also briefly study PDF, why it is so popular format. The first step in any information retrieval system is text tokenization, which means to convert the document into a sequence of tokens. What is a token? For English language documents, a token usually corresponds to a sequence of alphanumeric characters, but it may also encode structured information like XML tags or other characteristics of the text. So in English language, it is every token is a sequence of alphanumeric characters, mostly separated by space. The tokens are separated by space or any punctuation mark. Okay. For example, if I see here, for is one token, English is another token, language is another token, documents another token, and so on and so forth. Right? Now, whenever we want to tokenize any document, we need to understand the characters first. The first thing is to understand the characters. For understanding the individual characters, we need to know how they are encoded. I believe all of you are well familiar with the old ASCII format. Okay, it was only 7-bit format, so it could not handle more than 256 characters. But now we have Unicode, UTF-8, 16, and 32, which can handle all characters of the, I believe, all the languages in the world, right? So these are used to encode the individual characters. Like if I talk about ASCII, the ASCII code for capital A, I believe it is 65. Similarly, B is 66. See, every character has a code which is used to encode the character at the machine level, right? Talking about UTF, they use different encoding schemes like UTF-8, 16, or 32. Some of them are fixed length, some are variable length. You will also do a small comparison between fixed length and variable length encoding schemes in the Unicode. To tokenize the XML in figure 1.3, this one that we just saw before, we treat each XML tag and each sequence of consecutive alphanumeric characters as a token, right? So we treat each XML tag and each sequence of characters as one token. So this is one token, thunder is another token, this is another token, another, and so on and so forth. Okay. The next what we need to do, we convert uppercase letters outside tags to lowercase in order to simplify the matching process. Of course, in information retrieval, we'll be doing a lot of matching to retrieve any information. So to normalize the text, one of the basic operation performed is to normalize the case of the letters. So if there are any uppercase letters or any mixed words, sorry, not letters, or any mixed case words, we convert all of them to lowercase so that the matching process becomes simpler. And the next thing is each token is accompanied by an integer that indicates its position, okay, in a collection of Shakespeare's 37 plays. So here, like if it is the first play of Shakespeare, then this stage direction, its number is 1 in the entire collection. This is 2, this is 3, this is 4, this is 5, 6, 7, and so on and so forth. So every alphanumeric sequence is separated, including the XML tags, and it is assigned an integer number which shows its position in Shakespeare's 37 plays. So if we have 37 plays, let's say this is play number 1, this is play number 2, this is play number 3, and so on and so forth, till this is play number, till this is play number 37. So we start from first token in first play, like all these are tokens, okay. So we assign this as 1, the first word in first play, second word is assigned 2, 3, 4, and so on and so forth, till let's say the last word, it is assigned, let's say 1234. So we will continue. The first word in the second play will be assigned 1235 1236 and so on and so forth. Let's say it ends at 2000. Play 3 will start from 2001 and so on and so forth. So this is a very simple tokenization scheme. We start from first word, first token in the first play. We keep moving. Every token is assigned an integer number till we have reached at the last word in the last document. Let's say it is 32,767, something like that. Okay, the last word in the last play. So this is a simple tokenization scheme that we use. And we also consider the XML tags. It is in XML format. So they are also considered to be part of the document. Like here, state direction, its number is 745,396. Of course, there are many plays before this. So its number is this. This is 745,397 and so on and so forth. So it ends here. The next play it will start from onwards, right? So very simple and tokenization scheme. Vocabulary. The set of distinct tokens or symbols in a collection is called the vocabulary. Distinct, which means the unique tokens. In every document collection, many words will be repeated several times. So if we remove those repetitions and we take the unique tokens or symbols, then it is called the vocabulary, right? For example, if you see here, the is repeated many times in this document. The is repeated here, I can see it here, and that's it. So it is repeated 2 times, but in the vocabulary we will consider it only once. So it is one word in the vocabulary. Okay, so it is denoted as V. Our collection of Shakespeare's play has 22,987 symbols in its vocabulary, right? So the size of the vocabulary is 22,987. These are the unique words without repetitions in the place. Like you will assume that will be repeated several times in the place, but it is taken only once. Aaron, Abbasis, Zounds, Wagger, and so on. So all these, they are the unique tokens or symbols in the collection. So the unique or distinct tokens, they are called the vocabulary of document collection. So here you can see 20 most frequent terms in the XML version of Shakespeare's play. As you can see, line is the most frequent token because every line is encoded with the line tag, and in XML I believe you know that every opening tag must have a closing tag. So every line, if line appears these many times, the closing of line tag, it also appears the same number of times. Similarly, speaker appears this many times and the closing tag also appears same number of times. And if we ignore this XML, you see the first English language character, the most frequent one, it is the. So it is quite common that we use the quite oftenly in any document. So it appears 28,317 times. The second is and, 26,022, I, and so on and so forth. So these are 20 most frequent items in the document collection, this particular version, XML version of Shakespeare plays, and you can see their frequencies are given. There are 912,052 tokens in the Shakespeare's plays. Now I believe you understand the difference between the vocabulary and the tokens. So this number, it was this 22,987. These are the unique symbols or unique tokens, but if we consider the frequencies also, like the appears this many times and appears this many times, if we add up all of them, then the total number of tokens in the Shakespeare's play, they are 912,000. Now if we pick a token uniformly at random from these plays, let's say I just pick randomly, I say okay, I will pick a token at position 1235, or I'll pick a token at position 123. Okay, so if I pick any token at randomly, then I can calculate the probability of what this symbol might be. Okay, I can know the probability of a particular token, that this randomly selected token, it will be this particular token or symbol. Let's say if I want to see the probability of the, okay, the probability of picking the is simply the frequency of the divided by total number of tokens. It makes sense, right? So the frequency we have just seen in the previous slide, the frequency of the is 28,317, and the total number of tokens are 912,052. So we simply divide the frequency by the total number of tokens, the total size of the tokens in the entire document collection, and we can say that this is the probability of picking this particular time in term in the document collection. Of course, it's intuitive that the more frequent term will have a higher probability of being picked as compared to a less frequent term. Like the, it appears the most number of times in the document collection, like over 28,000, and on the other hand, Zweigert, it appears only one time. So if I pick any term randomly from the Shakespeare play, the probability that it is 3.1%, and the probability that it is Zweigert, it is just 0.00011 or 0.011%. Okay, if I multiply it by 100, right? So of course it makes sense that if we have the entire document collection, if I know the total number of tokens in any document collection, and I know the frequency of every term, I can calculate the probability of picking it at random. So you can relate it with simple probability, like if I have a coin, I'm sure you have studied basic probability, coin has only two sides, head and tail. Okay, so what is the probability of picking head? If I toss a coin, what is the probability that I'll get a head? Simply we divide 1 over 2, 50%, right? Because it is a fair coin. Or what is the probability of tail? It is also the same. Okay, but let's say if I have a coin with 2 heads and 1 tail, let's say, just for the sake of example, I have a coin which has 3 sides. On 2 I call them head and 1 I call tail. Then what is the probability of picking head? It will be 2 over 3, because head is repeated 2 times and tail is repeated 1 time, and the total number of possibilities, it is 3, right? So the probability of picking head will be 2 by 3, and the probability of picking tail is 1 by 3. Okay, let's say I'm talking about a coin with 3 sides, whose 2 sides are called head and 1 is called tail. Of course, we do not have any such coin, but just for the sake of example. Similarly, if I take the example of a dice which has 6 sides, okay, a dice has 6 sides. Okay, so this is 1, this is 2, this side is 3, this is 4. We have 6 sides. So what is the probability of picking 1? If I roll a dice, it is 1 over 6. What is the probability of picking 2? It is also 1 over 6. If there is a dice in which 1 appears, let's say 3 times, So what is the probability of 1? Then it will be 3/6. So we simply calculate the frequency, how many times something is repeated, divided by the total number of outcomes. So it's the same concept here. The total number of terms in the entire document collection is something like 912,000. For any term or any token, we can calculate the probability of picking it at random by dividing its frequency by the total number of terms. So simple so far? I hope so. Language model. Now imagine that a previously unknown Shakespeare play is discovered. Can we predict anything about the content of this play from what we know of the existing plays? Well, you will agree with me that if you read a lot about a particular author and I give you some piece of text and I say that, okay, this text is written by that author, you can say with some level of confidence, because you know that every writer has his own style. Every writer has his or her own style. So when you read a lot about it, now you can judge. If I give you a new piece of text, you can say with some level of confidence whether or not it might be written by that particular author, right? So language modeling is also about the same concept. We'll talk more about it in the coming slide. Prediction concerning the content of unseen text, we are talking about unseen text, may be made by way of a special kind of probability distribution known as language model. So we can develop a language model for any document collection, and then we can make some judgment about a new unseen text, about what it might contain. Okay. Some of the applications of language models, it can be used to quantify how close a new text fragment is to an existing corpus. For example, plagiarism detection. So for plagiarism detection, we may find similarity between an existing corpus, the collection of documents, and a new piece of text. This is one application. Another, suppose a new previously unknown play is found, expert debate about who might be its author. Author attribution, it is another application. Author attribution. So we have found some text and the people, they debate, okay, it might be written by Shakespeare, and another one say no, it might not be, it might be written by some other author. So what we can do, we apply the language models to compute the probability of the new text according to each author. So if we develop a language model for each author, now we can apply the language models to compute the probability of similarity between the new unseen text and the language model that we have developed based on the known pieces of writing. Like for example, for Shakespeare, we know we have his 37 plays. So from these plays, we can develop a language model, and then we can apply this language model on the new unseen text to measure the similarity. So what we do, we apply the language model to compute the probability of the new text according to each author. For Shakespeare, we have developed a language model. For the other authors, we may have developed language models. So the language model that assigns the higher probability to the new text may indicate its author. So the language model which assigns a higher probability for a particular author to this new unseen text, it can indicate that, okay, the probability that this piece of text is written by this particular author, it is higher. So we can say that with some level of confidence that it might be written by that author, right? I hope you get the basic idea. The basic idea is to capture the vocabulary and the style of any author and in the form of a language model, and to apply it on a new piece of text to calculate the probability of who the author might be for this piece of text. The simplest language model is a fixed probability distribution over the symbols in the vocabulary. It's a fixed probability distribution over all the symbols in the vocabulary. Can you read this equation in simple English language? Well, I have given you a link over here, okay, for the mathematical symbols. Just go through the list so that you should know which symbol is this. There are many Greek and Latin symbols used in mathematics, so you should know what symbol is this, what is this. So if I have to read it in plain English language, I will say that sum, this sigma is described as sum. It symbolizes summation, addition of certain things. Sum of probability, this is the probability of term small sigma, a particular term sigma. Sum of probability of all terms contained in the vocabulary V is 1. How can we read this equation? The sum of probability of all terms in the vocabulary is 1. It's very actually it's a very basic concept. Like if you talk about coin, okay, in coin we have two possible outcomes, okay, we have head and we have tail. The probability of head is 0.5, 1 by 2, 50%. The probability of tail is 0.5. So if I add them, I'll get 1. Similarly, if I take a dice, dice has 6 sides. The probability of every side is 6. So the probability of 1 is 6, plus the probability of 2 is 6, the probability of 3 is 6, 4, 5 and 6. So 6 times 1 by 6, it is also 1, right? So basically it's a simple probability distribution that the sum of all possible outcomes, it should be 1. It's quite intuitive, right? So this language model is a very simple language model which says that the sum of probability of all the terms in the vocabulary should be 1, and it's quite intuitive thing. You can apply it in any domain. Whenever we have any possible number of outcomes, the sum of all the probabilities of those outcomes, it should always be 1 or 100%, right? The sum of all of them should always be 100%. A language model is often based on an existing text. Okay. Just like for coin or dice, we know what are the possible outcomes. Similarly, in language model, we know what are the terms. Okay. If we do not know the terms, we cannot make a language model, right? So we have terms, we know their frequencies, and we can calculate the probability by dividing the frequency of each term divided by sum of the frequency of all the terms in the vocabulary. So it is simply the total number of tokens in the document collection, right? So like the appears 28,000 some times and appears, let's say, 22,000 some number of times, and so on and so forth. If we add up all the frequencies, what we will get? We will get the total number of tokens in the document collection. So just like for the coin or dice, for coin I know there are only 2 possible outcomes, head and tail. For dice, I know there are 6 possible outcomes, 1, 2, 3, 4, 5, 6. And just before, we were talking about a special coin, let's say it has 2 heads and 1 tail. So we know the total possible outcomes are 3. 2 head, the frequency of head is 2 and the frequency of tail is 1, right? So this is a very simple language model. It just considers the probability of all the terms in the document collection, in the corpus, right? Now if we pick a token at random from Shakespeare known play, the probability of picking the term sigma is m sigma. We have just seen before, like for the, we had calculated the frequency, the probability of picking the, we just divided the frequency of the divided by number of tokens. Let me take you back to that slide. It was here. So the probability of picking the, how we can calculate, frequency of the, which is 28,317 divided by total number of tokens. Again remember, this is not vocabulary, it is not vocabulary, it is total number of tokens, right? There is difference. It is not unique terms, it is the total terms considering all the frequencies of all the terms in the entire document collection. Okay, I hope it is clear for you. Maximum likelihood estimate. If we start reading the unseen play, we can use the language model to make a prediction about the next term in the text. Now we have just taken the example that we all know about 37 plays of Shakespeare, and now a new play is discovered. Now the people debate about whether it is written by Shakespeare or not. Now we can go, what we can do, if we start reading the unseen play, we can use a language model to make a prediction about the next term in the text. How? Based on this language model, the probability that the next 6 terms are to be or not to be, these are 6 terms. First is to, second is be, third is or, fourth, fifth and sixth. So what is the probability that the next 6 terms are these to be or not to be? So MLE can be used for this. What we do, we simply multiply the probability of all these terms together, and now we can say this is the probability that the next 6 terms, we can make a prediction that the next 6 terms are to be or not to be. The probability of 2 is 2.18%, or if you write in numbers, it will be 0.0218. The probability of B is 0.76%, or is 0.27, not is 0.93, 2 is again 2.18, and so on and so forth. So this is the probability that the next, if we start reading this unseen play, the probability that the next 6 terms are to be or not to be is this much. Maximum likelihood is a standard method for estimating unknown parameters of a probability distribution given a set of data. So if we are given a set of data, we can make a language model from that data, and then we can predict the unknown. We can predict about an unseen play, what it might contain. You will also study dependent and independent events and probability. Now any probability over a vocabulary of terms may be treated as a language model. You can make any language model with any terms that you like. You can make your own language model. For example, here we have made a language model that contains only 1, 2, 3, 4 terms. The probability of 2 we have defined as 0.4 or 40%. The probability of B is 0.3 or 30%. The probability of OR is 0.2 and the probability of NOT is 0.1. Remember, you can make any language model that you like, you are free to make any one, but the sum of all these probabilities must be exactly 1. Like if I add 0.4 plus 0.3 plus 0.2 plus 0.1, I get exactly 1. Okay. Of course, if you are making a language model on an existing text, it will always be 1. It can never be more or less than 1. But if you are making your own language model, you have to make sure that it always adds up to 1, right? Now based on this, let's say I have made this model which contains only 4 terms, to, be, or, not. Now based on this distribution, based on this language model, the probability that the next 6 words are to be or not to be is what? So first of all, probability of to be or not to be. So this 0.4 is the probability of to, this is be, this is not to be or not to be. I just multiply all of them together and I get 0.00029 or 0.029%. Based on this language model, the one that I have just defined, the probability of getting the next 6 terms are to be or not to be is 0.029%, while it was this much in case of the Shakespeare. Okay, for Shakespeare we had seen that the probability of getting the next 6 terms in unseen text is this. It's very, very low. Of course, because the probabilities of these terms were quite low, here we have taken them quite high. Well, one important thing in the language model is the unknown terms. Here I was calculating the probability of the next 6 terms to be or not to be. Let's say if I want to see the probability of next 6 terms as to be or not to be, let's say cat. Let's say this is my 7 terms, to be or not to be cat. Okay. Now I have put all the probabilities 0.4 for all these terms here, 0.4, 3, 2, 1. But the probability of cat, what is the probability of cat based on this language model? Of course the probability is 0, right? The probability of any term for any document collection in which it does not appear at all, it is always 0. Now the other terms, their probability might be quite high, but the probability of this one term which is not a part of the document collection, it will make the entire thing 0, right? Because this term, it does not appear in this language model. Okay. So what we do, we can, to avoid this 0, we can extend the vocabulary with an unknown symbol. So we add up the unknown symbol with the vocabulary and we assign this unknown symbol a particular probability. So I call it beta. Beta can be anything between 0 and 1. It depends on your own choice. Okay, you can define any value for beta. Now what we do, we revise all the probabilities of the existing terms in the document collection. So now, and any term which does not appear in the language model, it will be assigned this probability, so we will never get 0. The basic idea is whenever you are developing a language model, the unseen text will always have some terms which are not a part of your language model, which are not a part of the document collection, the corpus that you have. So to avoid making it 0, we can add an unknown symbol and assign it any probability, and now we have to revise all the probabilities of the terms by this formula. So we take the original probability and multiply with 1 minus beta, and now we will apply the new language model on the unseen text. Let's see how it works. For example, this is M, the probability of 2 is 0.4, B is 3, 0.2 and 0.1. These are the original probabilities. So we have just seen that if we add any new symbol which is not here in the prediction, it makes the entire thing 0. So now we assign this unknown symbol, the let's say the probability of unknown, we call beta, let's say I take it as 0.1 or 10%. Okay, I extend it with an unknown symbol, and the beta I take as 0.1, or you can say like 10%. Okay. So I have existing probabilities, and now I will revise all these probabilities. Okay, if you see here how we revise them, we have original probability and we multiply it. The original probability is multiplied with 1 minus beta to calculate the new probability. Okay, so now beta is 0.1, so the new probability of 2 is the old probability 0.4 into 1 minus beta, 1 minus 0.1. Okay, so 0.4 into 0.9, it will be 0.36. Okay. Similarly, the new probability of B is 0.3 into 0.9. This thing comes out to be 0.9, so it is 0.27. Similarly, the new probability of R is 0.2 into 0.9 is 0.18, and so on and so forth. So now if I want to predict the next terms as 2, B, cat, okay, what I will do, the probability, now the revised probability of 2 is 0.36 into the revised probability of B is 0.27, and the probability of cat is beta, it is 0.1. I can calculate it, you will get a number, you will never get 0. Or if you have more terms to be cat or dog, so the probability of R is 0.18 and the probability of dog is again the beta. So for any term which does not appear in the language model, in the document collection, we will assign it the value of beta that we have defined over here. So I hope it is clear for you. Today we have learned some of the basic stuff in information retrieval, the text, how we process the text, what are the basics of text, and then we have learned one technique, language modeling, and we have seen how we can capture the style of any author, the writing style of any author, by using language modeling technique, and what are the different applications of language modeling like plagiarism detection and author attribution. And then we learned how we can make predictions about unknown text based on the language model that we develop from the existing collection of text or any author. And finally we saw the use of unknown symbols which are not a part of the language model, and if we do not handle them properly, they will make the entire probability always equal to 0. So to avoid that, we can introduce an unknown symbol in the vocabulary, we can assign it any probability, and then the entire probability will never become 0. So inshallah in the next lecture we will talk about some of the basic stuff about algorithms, and then we will move to the more IR techniques. We will talk about indexing, searching, ranking, and the evaluation of information retrieval techniques. Okay, thank you very much. That is the end of the lecture. Assalamu alaikum wa rahmatullahi wa barakatuh.